Okay, so let's continue. Now I want to give you some measure of work in terms of the velocity of the object. So far, we have calculated the work only by using the force on the object and its displacement. But the next question is, can we express the work done on the object only by observing its change of velocity? Okay, and for this, imagine this scenario that we have a box, we have an object moving with constant velocity. Imagine that the object is moving on the surface toward right without any friction, so it will continue its motion if there is no force on it with the same velocity forever. Okay, but at the instant that when the object moves at a constant velocity, we apply this net force. Okay, and imagine there are no other forces, no friction, and we apply this force for a displacement of delta x. So application of this force will continue for as long as the object moves this distance delta x. So we can easily calculate the work done by the force. But the question is, what happens to the state of motion of the object during this displacement delta x? Will it continue its constant velocity motion, or will the velocity increase? Obviously, on the application of a force, if there are no any other forces, we will have a non-zero net force. If you apply a non-zero net force to an object, the object will have a non-zero acceleration, right? So, as soon as you start applying this net force on the object, which moves initially with a velocity of v0, since it will have a non-zero acceleration by the Newton's second law, because F force is equal to m times a. If force is not non-zero, then a necessarily will be non-zero. So the object will increase its speed, right? When going a distance delta x, the object during this time or displacement will increase its speed. So until the end of this displacement, the velocity will be increased to a final velocity which is larger than the initial velocity v0. And during this motion of delta x, we can write down the relation between the final and initial velocities by using the kinematics equation from the chapter 1 to second chapter. And if you know the initial velocity, if you know the final velocity, if you know the displacement, and if you know a, the acceleration, the formula that you are going to use is this one. All right? Remember this formula. The final velocity squared is equal to initial velocity squared plus 2 times the acceleration times delta x. So I can express a, the acceleration time delta x, in terms of the initial and final velocities. That's what I do in the first line. So a times delta x is equal to final velocity squared minus initial velocity squared divided by 2. And it is necessarily a positive quantity, so v final is always larger than v0. So the application of this force certainly increased the speed of the object. The question is, can I express this work in terms of velocities? Next, we know that the work done is the force on the object times delta x. But what is force in terms of the mass and the acceleration? It is just m times acceleration, right? You see, instead of force, I can write m times a by the Newton's second law. But when you see this expression in total, m times a times delta x, observe we have an expression a times delta x. But a times delta x, previously I have expressed in terms of the initial and final velocities. So I can use this term in here, right? And I can use this m times, instead of a times delta x, I use the final velocity squared minus initial velocity squared divided by 2. So what you obtain, the work done by this force is 1/2 mv square, v final square, minus 1/2 mv initial square. So the work is some quantity after the force is applied minus the same quantity before the force was applied initially. So we have 1/2 mv square minus 1/2 mv0 square. What is 1/2 mv square? In physics, this term, this expression, is known as the kinetic energy of the object. If an object which has mass m is moving with some speed, then this object is said to have a kinetic energy of 1/2 mv square. So you see, the work done on this mass can be expressed as the change in its kinetic energy, because 1/2 mv square is the kinetic energy after the force is applied, but 1/2 mv0 square is the kinetic energy before the force is applied, just before. So we can express work done on the object as the difference of its kinetic energy between the final and initial points. So the work done is nothing but the change in the kinetic energy. Even if you don't know the force acting on the object, just by observing its change in the velocity, you can calculate the work done on the object. Okay? This is called the Work-Energy Theorem. And the Work-Energy Theorem says the work done on a system or on an object is just the change in its kinetic energy. The work done on it is equal to, let me write it down as delta. We usually denote the change as delta KE. Kinetic energy sometimes is expressed as just K with capital K, not KE, but they are equivalent to each other. Okay. So an example. And suppose you are moving with your car with some initial velocity, and you have seen another truck in front of you before. To avoid hitting this car, the truck, you push your brakes, and you push your brakes for a distance x, and your car comes to a stop after you apply the brakes at a distance. The question is, at what minimum distance should the brakes be applied to avoid the collision? So you push the brakes for some distance, and this distance is required, and if the car is initially moving with some constant velocity vi, and the mass of the car and truck is given 1 tons, 1,000 kilograms. Initially the car is moving with 35 meters per second. This is vi, and when you push the brakes, of course, the force that stops the car will be the frictional force between the tires of the car and the surface. Okay, let's try to find it. Before you think about this problem, you have to apply the work formula, the force of friction times the distance. But if you think that you are given the initial and final velocities, because initially the velocity is 35. Finally, the car stops, the final velocity is 0. So you can express the change of kinetic energy between these two situations that by using 1/2 mv final square minus 1/2 mvi square. But you know the final velocity is 0, So the final kinetic energy is 0. And the total work done on the object must be a negative quantity because we have minus 1/2 mvi square. And these terms are always positive. So the work done by the friction must be equal to this quantity, right? But to calculate this quantity, you observe that we haven't used the frictional force. We only used the initial and final velocities, that's all. Okay. The next question is, what is this distance? Delta x. Okay. And the distance is asked because the frictional force is given. Okay. The frictional force is given. You haven't used this frictional force in calculating the first part because you didn't need it. But in the second case, if you are asked to find the stopping distance, delta x, then there is only one way to find it. This force of friction times delta x must be equal to the work done by the frictional force, which we have calculated in the first part. So we can write minus Fk times delta x is equal to this quantity. But I know Fk is given as 8,000 newtons, 8 tons. So I can solve for delta x. I can find the stopping distance just by dividing the total work done by the frictional force by the frictional force itself, 8,000. And you will find 76.6 meters. So by using the Work-Energy Theorem, you can find the stopping distance because you know the initial and final velocities, and you know that these are related to the work done by the frictional force by the help of Work-Energy Theorem. In the second case, it says if the distance between the car and track is given as 30 meters, then what speed should the collision occur? Okay. And from the first part, we know that to avoid the collision, at least we need this much distance between the car and track, 76.6 meters. But if the distance between them is 30 meters, then what is the collision velocity of the car? It will definitely collide because there is not enough space between the cars. So again, this time we will calculate the total work, okay, by two different expressions. First, by the force of friction times delta x, okay, because I need to know what the work done by the friction, and it is simply the frictional force times 30 meters. We have to put minus sign because the force is in the opposite direction with the displacement. And during this distance, 30 meters, the work done by the frictional force is minus 2.4 times 10 to the 5 joules. But I know the initial energy, kinetic energy of the car. So I know initially the car has 1/2 mv final square. But if I subtract this 1/2 mvi square, sorry, I know the initial velocity, not the final velocity. I know the total work because the total work done is just this minus this one, the work done by the frictional force. So I can express this 1/2 mv final square in terms of the sum of these two different forces. This, sorry, force, not forces, not the works. This minus work is done by the friction, and this is the total work needed to do to stop the car completely. If you add them all and equate the 1/2 mv final square, you can express V final. You can find the V final because you know the mass of the car, and easily you can find this collision velocity as 27.3 meters per second. So you just calculate the total work done by the total work of the car to be done on it to stop the car, minus the work done by the friction during this 30 meters distance. You can find this quantity, this difference, which is equal to final kinetic energy of the car, and from this you can easily pull V final. So this is also one application of the Work-Energy Theorem. So you use the Work-Energy Theorem to find the final velocities, the initial velocities, to find the velocities, and also you can find the distances. Okay, if you know the forces of friction and others. The same information you can in fact find the final velocity by using the kinematics, right? The kinematics of chapter 2, and we know the final and initial velocities are related to each other by v final squared is equal to v0 squared plus 2 times the acceleration times delta x. And you can find the acceleration of stopping acceleration by using the force of friction, because the force of friction is equal to m times acceleration, and you know the mass of the car, you can find the acceleration. So the same quantity, the final velocity, you can also find by using the kinematics equation, not the work equation. But now there are many ways to calculate the velocities, distances, and everything. Now this new method is to use the Work-Energy Theorem. Okay, I will stop for today to let you concentrate on the exam. And if you have questions about the exam or problems, then you can ask me.